Welcome back to another video. By now we learned about martingales and about the stochastic integral. And the martingale property is a property between fixed time points s and t. And now we're going to ask ourselves if the same property also holds for random times. So if you have two random times, s less or equal to t, two are random, is it then also true that this martingale property holds between s and t? Okay, let's do it. And this question is actually a question about stopped martingales. And we already know what stopped stochastic processes are, but let me recall this. So this slide here is very general. X is just a stochastic process in F is filtration. And we already know that a random time is a random variable which has values in the index set, maybe also including infinity. And we call a stopping time a time with this property. So the stopping time less or equal to small t is in ft, which means the event that the stopping time has occurred at or before time t can be decided when I know everything up to time t. This stopping time defines a sigma algebra, which is this one here, F capital T, which we already had. So that's the defining property. So a set is in this sigma algebra here, if and only if the set intersected with the stopping time occurring before or at time t is in ft. Very often these stopping times are hitting times, which means tb is the infimum time where xt is in b. We already had x index t, and we asked ourselves in the progressive measurability video if that is a random variable, and the answer was if x is progressively measurable, this here is a random variable, which means it's measurable. That was one lesson. The other thing we had is that x superscript t, that's the process stopped by time t, like this here. Sorry, here something went wrong on the slide. So if x is adapted and I is countable, then basically a stopping time is a the stopping time, which the hitting time of any Borel measurable set is a stopping time. So like this. So when we have discrete times, then hitting times are stopping times. So you're safe to think about stopping times as hitting times. And that they're just a very nice example. So, first of all, we can have a martingale, x, and we can ask ourselves, if I stop this martingale at a stopping time, does it stay a martingale? And the answer is yes, and that's the optional stopping theorem. The same holds true for sub and super martingales. So let's prove the thing for sub martingales. And the same holds then also for super martingales. And since a martingale is a super martingale, which is also a sub martingale, it then also holds for martingales. So proof for sub martingales. What do we need? We need to see that x by time t minimum small t minus x big T minimum t minus 1. So that's the stopped process, the increment of the stopped process. I want to condition this here on ft minus 1. And actually, if the stopping time here happened at or before time t minus 1, we have a 0 here. because then the minimum is capital T in both cases. So this here is the same as restricting the difference to the case where big T is bigger than T minus 1. Like this. Of course, this here is the complement of big T less or equal to T minus 1, and therefore is Ft minus 1 measurable. So I'm safe to pull this out, but on the other hand, on the event that T is bigger than T minus 1, I'm safe to exchange these things here for T and T minus 1, because these are the minima. So now it makes sense to pull this out here. xt minus xt minus 1 given ft minus 1. And this here, of course, because x is a submartingale, is bigger or equal to 0. And that means we have shown that the stopped process here is a submartingale. And we are done with the optional stopping theorem. That was our first result. Our second result is very much like what I introduced in the intro. We know if we would write here a small s instead of a capital T and small s less or equal to small t, and if x is a martingale, then this here is true. The question is, can we replace this fixed time small s by the random time big T, which is less or equal to small t? And the answer is yes, that is true. First of all, x capital T, that's a random variable, because since I is just a discrete set here, every process is progressively measurable. xt is measurable with respect to f capital T. We showed that in some earlier chapter, and f capital T is a subset of f small t because of this here. We also showed that in a previous chapter. We need to show the following. I claim the expectation of xt on some set A equals the expectation of x big T on the same set A for all A in Ft, which is the sigma algebra of the big T past. Why does this suffice? So xt is Ft measurable anyway. And by definition, so what's this random variable here? That's the unique Ft measurable random variable, such that the expectation of xt on some set A equals the expectation of this random variable on A. So using this characteristic property of the conditional expectation, when we have shown this here, we have shown the property that we want. So let's start. Expectation of xt over A. What can happen? Okay, many things can happen. We know that capital T is smaller or equal to small t, and we can split up everything. To all cases that can happen. So from 0 to t. And I have an xs on the set t equals s and a. Well, t equals s and a is in ft, so when is a in ft? It's in ft if this thing here, okay, with less or equal, but it doesn't really matter because this set here is the same as less or equal to s without s less or equal to s minus 1, which is also an element in fs. So that means this set here is in fs by definition of the sigma algebra f capital T. So I can do this here. That's in fs, yes. And I can use again the defining property of the conditional expectation, and instead of xs, write the expectation of xt given fs. By the way, I'm only using here the martingale property. In this step, t equals s intersected with a. And now I'm using the property of the conditional expectation, that this thing here has the unique property that I can replace the whole thing by xt. Sorry. S equals 0 to t. Expectation of xt on the set t equals s intersected with a. And now I have to pull everything together, though I'm summing over all cases of s. So this here goes away, and I will have the expectation of x small t over the set a, which is exactly what I wanted to show. So I'm starting here from the right-hand side, and I'm ending with the left-hand side, and that's what I wanted to show. So we are done. And so you see, we have replaced a fixed time, small s, by a random time xt. And what we now want to move to is the optional sampling theorem. The optional sampling theorem, we have it a bit more general. We have two random times s and t, and we want to have still that if x is a submartingale in this case here, the submartingale property also holds along random times, stopping times. It won't be that general. Something can go wrong, but it cannot go wrong if either t is bounded or x is uniformly integrable. Then this thing here holds. So we're going to move to this. But in order to do so, we need the following lemma. So if x is a martingale, it's uniformly integrable if and only if, it's stopped version. So x at a random time. That's a huge family, actually, because you can plug in here any almost surely finite stopping time. This huge family here is uniformly integrable. So from right to left, that's easy because all fixed times are of course almost surely finite stopping times. They're all within this set here, and if they're uniformly integrable, the left-hand side is also uniformly integrable, so that's okay. The interesting part is from left to right. And here I recall one theorem about uniform integrability, which was uniform integrability is the same as having a function from R plus to R plus, which is convex, and f of x divided by x goes to infinity as x goes to infinity, and the supremum over all t expectation f of xt. Yeah, let's call this L, and this is finite. So this here we know from uniform integrability of x. And we will use the same function f in order to show uniform integrability of the right-hand side. So that was a theorem which we learned about in the lecture on uniform integrability. Let's now take a stopping time. And our goal is the following: to show that the expectation of f of, well, absolute value of xt, I forgot this here, like so, on the set big T lesser or equal than small t. This here is smaller or equal to L. That's what you're going to show. Because once we have this, we can let small t go to infinity on the left-hand side. By monotone convergence, we get that the left-hand side converges to the expectation of f of absolute value of x big T. And we can then make a supreme over all stopping times t here. And then we have the same property, but with all stopping times here instead of the fixed times here, which shows that the right-hand side here is uniformly integrable. So that's what we want to show. Yes. First, we can, instead of writing x big T, we can write x big T minimum small t. And the reason is that we're on the set t lesser or equal to small t anyway. And since big T minimum small t is again a stopping time which is bounded from above by small t, we can use this property here. Which means expectation f of conditional expectation of x small t given f big T minimum small t on set big T lesser or equal than small t. And now f or f and the absolute value here composed, that's a convex function. And a convex function of a conditional expectation here, we have Jensen's inequality, which tells us it only gets bigger than when we replace f and conditional expectation. Expectation of f of like this here on the set ft minimum small t, and this here on the set big T lesser or equal to small t. Well, and this set here is in f small t, which means we can replace the first thing here with the conditional expectation by the same thing, but with f of xt on the set big T lesser or equal than small t. And now I'm done, because this thing here is by assumption bounded by L. And well, I don't really care about this, it only makes things smaller, so that's less or equal than L, and we are done with this thing here. And we can come to the optional sampling theorem, which is quite an important result, which shows how to replace the fixed times s and t by the random times, stopping times s and t, if we know that either t is bounded or x is uniformly integrable. Then since we have two assumptions. T is bounded. Let's first assume that t is bounded. T is bounded by some small t. Here it is for submartingales. So we first select an M and an A in the dupe decomposition. M is a martingale. M is a martingale, and A is a previsible non-decreasing function. Then we have xs equals ms plus as at the stopping time. Well, we first have that ms is m small t conditional on fs because of the other result that we had. mt plus as. Since x is a submartingale, a is non-decreasing, which means we only make it larger if we say that's not plus as plus but plus at given fs. And I replace mt by the conditional expectation of mt given f big T. I can also do this. Why can I do this? Because fs is a subset of ft. And yes, fs is a subset of ft. And the expectation of the conditional expectation, well, this thing fs here remains, so it's the same as this here. And this here now, here we're using the property that we had before, that this here is m index capital T plus a index capital T given fs, which is exactly what we want because this here is x at the stopping time t. And we are done in this case. So that was one of the two proofs. Now we need a second proof in the case where x is uniformly integrable martingale. If x is a uniformly integrable martingale, we know that xs minimum t and xt minimum t, where t ranges through all of I, is uniformly integrable because of the result that we just had, that this here is the same. Then what do we need to show? We need to show that the expectation of xt on a set A which is in fs is the same as the expectation of xs on the same set A. Because once we have this, we are using the defining property of the conditional expectation to see that xs here is the same as the conditional expectation of xt given fs. Okay. First, I want to write this here as a limit. For small t goes to infinity, the expectation of xt minimum small t on the set S lesser or equal to small t intersected with A. As you see, as small t goes to infinity, this function here goes to this function. So there's an almost true convergence of this thing here to this. But why can interchange the expectation and the limit? That's by uniform integrability, as we know. Because when the thing we are integrating over is uniformly integrable, we can exchange the expectation and the limit. Because then the L1 convergence follows from the convergence in probability, and this thing here converges to this almost surely even. So by uniform integrability, it also converges in L1, which means exactly this equality here. Okay, lim t goes to infinity. I have the expectation of the conditional expectation of xt minimum small t given fs minimum small t. Why is that? That is because this set here, A is in fs, A is in fs, which means that this intersection is also in f indexed small t. So this here is in f small t intersected with fs, which is fs minimum small t. And on these sets here, I can exchange the random variable by its conditional expectation. So on the same set, S lesser or equal to t intersected with A. And now I have two random variables, fs minimum t and xs minimum t and x small big T minimum t. And we already showed the optional sampling theorem for bounded t, and that t here is bounded such that I can replace this thing here by xs minimum t over the set s lesser or equal to t intersected with A. Well, and if you now let t go to infinity, again we have the L1 convergence from the almost true convergence from this to this, and we are done. Okay, great. So there are one or two more things. So one characterization of martingales here and two examples what we can do with all this left for this video. So first, a characterization of martingales. That's a very surprising one, I think, which is as follows. A process is a martingale if and only if its expectation is the same for all stopping times s and t, which only take two values. So they are bounded, they only take two values, and their expectation is the same. And that's an application of the optional sampling theorem, because, okay, they take only two values, so they are bounded. The optional sampling theorem tells you this here with an equality. And if you write an expectation to the left and an expectation to the right, you get that their expectations is the same. So this is clear from the optional sampling theorem for the one direction. And for the other direction, I wrote it down here. take an arbitrary set A in Fs and this stopping time here. S index 1, that's S if A occurs and T if the complement of A occurs. A is in Fs, so by time S it can be decided if, so the usual thing, so T less or equal to S can be decided using information in Fs. Okay. And when you do this, we're going from right to left, so this here holds. So this difference here must be 0. Okay, expectation of xt is here, and the expectation of x capital T. There are two cases. Either A occurs, then I have an xs here, or A does not occur, then I have xt here. And, well, something goes away. So this here stays, and expectation of xt minus expectation of xt on the set A complement is the same as the expectation of xt on the set A. And since A was arbitrary, we know that here something happens. So the conditional expectation of xt given Fs, it must be xs. So x is a martingale. So that was this thing here. Now there are two more applications of this optional sampling theorem. And the first one is as follows. So Waltz identities. So S is a sum of x's, as we often have for martingales or super martingales, and they all share the same expectation. And T is a stopping time. Then, well, you sum up all these x's until the stopping time T. And the question is, what's the expectation of S at the stopping time T? And the answer is, it's mu times the expectation of T. And T does not have to be independent of the x's here. So this here just holds. Why is that? Mt equals St minus T times mu is a martingale. And since this is a martingale, and T here is a bounded stopping time, we can use the optional sampling theorem in order to see that the m at random times is also 0, which shows this thing here, and m at time t, that must be the expectation of st minus expectation of t times mu, because that's just how it is defined. And we are done. So that worked for the expectation, and now you want to compute something on the variance. So assume they all have the same variance, and now t must be independent of the x's. Then the claim is that the variance of st, well, there are two terms. The expectation of t and the variance of t goes in here. The expectation of t goes with the sigma square, and the variance of t goes with the mu square. And the reason is, well, now we consider the martingale mt minus the square bracket process. And the square bracket process, so the increasing process, is, we computed this as t times sigma square. And that means that this thing here, and also the random time t, must be the same as the expectation of m in capital T square. So this thing here, because this here is a martingale. And mt square, okay, that's st minus t mu square. So this here is a random variable just a moment, something is wrong here. Mt t square. So mt square is the expectation of st minus t times mu square. But when I write variance here, I have to get rid of the square here, of course. And now I need that t is independent of s. And I get this thing here. Because the variance then just splits into the two things here. Well, not quite, not so fast. No, not really. Not really. It's a bit different. I need to compute the variance of this thing here, which is the expectation of the square. Maybe it's just better to write it like this. With the expectation here. Then I have the expectation of st square. I have minus the mixed term, which is something. Wait. So, in order to be a bit more precise here. So what's the variance here? Let's start from the right. So st that's just the sum. Yeah, so this is just the sum. So that's the expectation of st square minus the expectation of st square. And this expectation here of st square, that's this thing here, expectation of t square times mu square. And this variance, of course, is also the expectation of t square minus the expectation of t square. And as we see here on this side, I have minus expectation of st square. So that's mu square times expectation of t square. And the same is here. So these two terms actually go away. So then I end up with expectation of st square minus mu square expectation of t square. Yeah, and that's what this here is about. So when you multiply this, you need that t and st are independent. And then you see that by computing the square here, you get st square, you get mu square t square, and you get 2 times st t mu. And since they're independent, you get a minus 2 times something plus this thing here, and you end up exactly with this what's written here. Okay, these were these Wards identities. And the last thing here is this ruin problem. Maybe you already know this from some Markov chains which you heard about. Here it's as follows. So you have either zero money, so you're bankrupt, or you have n money, which means the bank is bankrupt. You start with, let's say, amount k, and either you gain money with probability P, or you lose money with probability 1 minus P. And you do this until you either hit N or 0. And the probability to go up is P, and the probability to go down is 1 minus P. So as written here, up is P, and P equals 1 minus Q, so Q is the probability to go down. T is the time when you are either rich or bankrupt. And pk is the probability that you will eventually be bankrupt. Then I can compute pk, the probability to go bankrupt, depending on p. And that's the formula here. And the reason is that this thing here, expectation of q over p to the power of x1. Let's compute this. So that's q over p if x1 equals 1. That happens with probability p. And if x1 is minus 1, you have p over q here times q. Okay. And then everything cancels. The p cancels here, the q cancels here. Q plus p is 1, and that's 1. And that means that if you multiply all these things for different indices here, you get a martingale. Because you're multiplying things which have expectation 1. So this here is a martingale. It is a martingale. And that means you start the martingale by q over p to the power of q. Since it's a martingale, the expectation is constant, which means it's the same at time 0 and at time t. But at time t, its expectation is, well, you're either bankrupt, probability pk. If you're bankrupt, the value here, the t here must be here, of course. If you're bankrupt, you have 0 here, which means you have 1 here. Or you're not bankrupt, you have n, then you have q over p to the power of n. Okay, and then you can solve this equation here for pk, and you get exactly this formula here. So that's the rule problem. Okay, very nice. So we are done with the optional sampling for today, and we will slowly but surely go to convergence results of martingales. Let's see what it means in the next video. Hope to see you then.